Hmm. Faithfully conveying value by interpreting great books from around the world. Oh, hello! This is Sally speaking about books. Today, we're diving into the book Pale Blue Dot, subtitled Exploring Humanity's Space Home. Back in 1990, Voyager 1, an American unmanned probe, captured a famous photo as it passed Neptune and Pluto. In that photo, a ray of sunlight cuts through the dark, and you can barely see a pale blue speck. That's our Earth. That's where the book's title, Pale Blue Dot, comes from. It's a book on the history of cosmic ideas, telling how our view of the universe has evolved. The book's by Carl Sagan, a famous American astronomer who directed the Planetary Studies Lab at Cornell and worked on U.S. space missions for years. He made key breakthroughs in planetary physics and was a globally celebrated science popularizer. In the 80s, he hosted Cosmos, a big science show that got translated into 10 or more languages, aired in 60 or more countries, and seen by over 600 million folks. He penned over 10 science books, and Pale Blue Dot is one of them. First published in 1994, it became a New York Times and Amazon bestseller, stayed hot for 20-plus years, and is seen as a top influential science book of the 1900s. New York. In the book, Sagan traces how our cosmic view shifted and nails down today's space exploration problems. Where should we go from here? Now, I'll break down the book's key points into 3 questions. First up, how did our view of the universe change? Second, what's been achieved in space exploration today, and what issues are there? Third, where should space exploration go next? First, let's tackle question 1. How our cosmic view evolved. Back in ancient days, people learned about the cosmos by just looking up. Watching the sun and stars rise and set, folks naturally thought Earth was the universe's center. This basic idea got shaped by thinkers into the geocentric model. Like in ancient Greece, Plato and Aristotle thought Earth was the center. Ptolemy, the ancient Greek astronomer, was the mastermind behind the geocentric model. Ptolemy realized Earth was spherical and thought it stayed fixed at the center of the universe. Outside Earth, he imagined crystal spheres of different sizes with celestial bodies attached. Their spinning made everything move. Later, the geocentric theory got mixed with religion, becoming this unchallengeable truth. For example, Christianity teaches that God created the universe, put Earth at its center, and had the sun and stars circle it. Oh, and God made humans, crowning them as Earth's noblest species. Some rulers used the divine right of kings idea to claim their power came straight from God or gods, just to cement their rule. They pushed religious teachings hard, making this Earth and human-centered view deeply rooted. But hey, are Earth and humans really the center of the universe? After Copernicus, that belief started to crumble. As we at Sally's Book Talks covered in 1543, astronomer Copernicus published On the Revolutions, proposing the heliocentric theory, kicking off the modern science revolution. Copernicus found that putting Earth at the center made planet orbits super messy. Their paths were chaotic, like headless flies spinning and circling around. But if you put the sun in charge, with Earth and planets orbiting it, their paths smoothed out to near circles. After Copernicus pushed heliocentrism, many folks began doubting Earth's centrality. By the 18th century, discoveries like aberration of light and stellar parallax rocked the geocentric model even more. In 1725, British amateur astronomer James Bradley discovered aberration of light. That's light travel difference. So, what's aberration of light? Picture this. You're standing in rain with no wind. Drops fall straight down on you. But if you walk forward, drops hit you from an angle. The faster you go, the steeper the slant. Bradley discovered that starlight hitting Earth also comes at an angle, slanting in. That's aberration of light. 12 years later, stellar parallax was also found. So what is stellar parallax? Hold out a finger in front of you. Look at it with one eye. Then close that eye and open the other. With the other eye, you'll see your finger's position shifts. That's parallax, because your eyes are in different spots. When Earth moves to opposite sides of the sun, folks see stars' relative positions change. That's stellar parallax.
Since stars are super far away, stellar parallax is tiny, but astronomers spotted it in 1737. Oh, the finds of aberration and parallax proved Earth's always moving and not the universe's center.
As telescopes got sharper, people saw beyond our solar system, billions of stars like the sun making up the Milky Way. And beyond that, there are billions more galaxies like the Milky Way. Through telescopes, folks also spotted other planets in our solar system and their moons. Some have atmospheres, mountains, ice caps, and clouds, kind of like Earth. So, Earth's really not special. It's small and ordinary in the universe. Since Earth isn't the center, are humans special in the cosmos? For ages, anthropocentrism, the idea humans are central, has been deep-rooted. Religious texts like the Bible say, a creator made humans to rule Earth. Plus, since modern times, humans conquered nature, becoming Earth's top species, making people think they're unique in the universe. But in the mid-19th century, Darwin's evolution theory showed species evolve into others. Humans came from animals, not a creator, nothing special, and the universe wasn't made for us. All right, we've wrapped up the book's first question. How did humanity's cosmic view transform? In ancient times, human stargazing mixed with philosophy and religion sparked geocentrism and anthropocentrism. Since modern times, the Copernican revolution and Darwin's evolution theory gradually made people realize Earth and humans aren't the universe's center. This cosmic perspective shift hugely boosted space exploration. Human knowledge of outer space keeps advancing rapidly. Now, let's dive into the book's second question. What achievements has human space exploration made, and what problems exist? Since the 1950s, folks weren't satisfied with ground-based telescopes anymore. They started flying beyond Earth to study what was once only seen through lenses. Two main reasons. First, even with advanced telescopes, it's hard to spot distant objects or see details on planets and moons. By sending probes close to these bodies, we can confirm telescope findings, like atmospheres, mountains, and ice caps. Second, ground observations have blind spots. For example, the moon always shows one face to Earth. Only probes can see its far side. Sagan believed the key achievements since the 1950s were, first, sending unmanned probes to study major planets and moons up close. In 1962, America launched the Mariner program. Mariner 2 went to Venus. And that same year, the USSR's Mars 1 headed to Mars, kicking off planetary exploration.
The most famous probes? Voyager 1 and 2, launched by the US in 1977.
Originally part of the Mariner program, they were later renamed Mariner 11 and 12. Launched 2 weeks apart, they had slightly different speeds and paths, but aimed to fly by gas giants Jupiter, Saturn, Uranus, Neptune, and their moons for close-up studies. Beyond these missions, both probes were tasked with leaving the solar system to contact extraterrestrial life. Oh, these probes carry images of Earth and humanity, plus human music like China's ancient piece High Mountains Flowing Waters, and greetings in 55 languages. So, for example, the English greeting says, "Children of planet Earth, extend their greetings to you." Through exploration, we've found Earth's environmental features exist on other planets and moons too. Take atmospheres. Our neighbor Venus is wrapped in a thick one. Its atmospheric pressure is 90 times Earth's. And many moons have atmospheres too, like Io, Ganymede, Titan, and Triton. Titan's atmosphere thickness is closest to Earth's. Plus, its main atmospheric gas is nitrogen, same as Earth. But Titan's air lacks oxygen and CO2. It's packed with ammonia instead. Now, mountains, volcanic eruptions, help form Earth's ranges. Probes found volcanoes on rocky bodies like Venus, Mars, and our moon, with Mars's mountains resembling Earth's most. In 1971, America's Mariner 9 reached Mars. It spotted 4 red spots. Scientists were puzzled since they had holes. When dust storms cleared, wow, they were massive volcanoes. The tallest, Olympus Mons, named after Greek god's home, stands over 25 kilometers high, doubling Mount Everest. Boom, boom. Like Earth, early Mars was a lava-covered sphere. Volcanic activity shaped its rugged landscapes. Earth's polar ice caps aren't unique either. Triton has similar shiny caps at its poles. But Triton's among our solar system's coldest bodies. Below 200 degrees Celsius, its caps are nitrogen, methane, and hydrocarbons. While Earth's freezing or thawing is physical, Triton's involves complex chemistry, forming tholins, reddish organic compounds that create beautiful surface streaks. Finally, let's talk about weather changes. They exist on other planets and moons too. For example, Titan has weather like rain and snow, but here it's not water. It's liquid or solid hydrocarbons. Titan's called the solar system's petrochemical factory, with rivers, lakes, and seas flowing with ethane and other organics. Of course, these planets have no life. Earth's the lucky one. At some point, it had the right temperature, ample water, and oxygen, conditions for life to thrive. Sagan believed that with future tech advances, we could terraform some of them to become human homes. Beyond unmanned probes, the second big achievement in human space exploration is manned spaceflight. In 1961, Soviet cosmonaut Yuri Gagarin orbited Earth in Vostok 1, becoming the first human in space. Humans can stay long-term in orbit and perform spacewalks. And America's Apollo program landed humans on the moon for the first time in 1969. Though the moon has no air, no water, and no signs of life. But Sagan thought the moon landing didn't just teach us about its makeup and history. It was the first step in building off-world homes. This proves establishing homes beyond Earth is technically feasible, just needs more money and time. When humans first launched spacecraft, some still thought space was layered with crystal spheres. They even warned that entering space would shatter the spheres with a crashing sound, but of course, no one heard it. Even so, some subconsciously cling to anthropocentrism. For instance, Sagan got a letter from a reporter writing, "Maybe we're embarrassingly related to monkeys. But at least we're the best beings. Besides God and angels, we're the only intelligent life in the cosmos. Thus, humans deserve to reclaim their place as the universe's center." Sagan believes some refuse to abandon anthropocentrism not just for superiority, but to excuse plundering Earth's resources and killing species. He worried more that anthropocentrism breeds narrow local centrism. Ethnocentrism drives wars between nations fighting over land, essentially putting themselves as superior centers deserving more resources. And the rapid space exploration in mid-20th century was fueled by US-Soviet rivalry. Though both claimed a peaceful space use, their space race was fundamentally this narrow local centrism. Ethnocentrism became a space competition where few fought for their own interests. Technically, rockets launching spacecraft originated from warfare. Modern rockets evolved from Germany's V-2 missile, developed in 1942 for war. Post-war division narrative. The USSR got V-2 research data while America got its lead scientist, rocket pioneer Wernher von Braun. The US and USSR separately developed space-capable rockets. In 1957, the USSR launched Sputnik 1, Earth's first artificial satellite. The next year, America sent its satellite to space too. This race reeked of gunpowder.
US President Nixon even proposed armed astronauts in orbit to shoot down Soviet satellites and missiles.
Later, Reagan's Star Wars program aimed to extend battlefields to space.
The 1950s to 80s saw intense Cold War rivalry and the fastest space exploration progress. By the 1990s, when this book was written, the USSR collapsed, Cold War ended, military tensions cooled, slowing space exploration momentum. All right, we've covered the book's second part. Since the 1950s, human spacecraft have reached all major planets and moons in the solar system, sending astronauts into orbit and to the moon, taking the first step toward building a space home. Oh, though the Cold War ended long ago, space exploration today isn't just science, it's part of national military strategy. But Sagan thinks military conflict shouldn't be the main driver. Oh, all right, now let's tackle the book's third question. Where should future space exploration head? In Sagan's view, The goal of future space exploration should be sending humans into space to find new homes for humanity. There are two reasons why humans need to find new homes. First, migration and expansion are human nature. We're wanderers at heart. Earth's earliest life forms likely came from space, originating from comet impacts. 2 billion years ago, human ancestors lived in oceans, gradually migrating to land through evolution. Even hundreds of thousands of years ago, when true humans emerged in Africa, they didn't stay put. They migrated everywhere seeking better environments. Today, most folks settle down, building cities and nations, calling them homelands. This creates the illusion that we can't leave our homelands. But with population growth depleting Earth's resources, humans will inevitably wander again. Leaving for space is our future must-do. Second, to dodge disasters and avoid extinction. Migrating to other planets is a practical need for humans. Besides resource depletion, humans could face global catastrophes making Earth unlivable.
For survival, we must find new homes to prevent extinction.
Like a runaway greenhouse effect. With fossil fuel use, massive CO2 emissions are slowly hiking Earth's temperature. Though Earth has some temperature control, it could spiral out of control beyond a point. What are the consequences? Venus is a prime example of runaway greenhouse effect. Its atmosphere is 97% CO2, surface temperature over 400 degrees Celsius, like a hell on Earth, even if humans cut emissions. But interstellar collisions are hard to avoid artificially, and they're not rare for Earth. Scientists found Earth gets hit by asteroids over 70 meters wide every few hundred years on average. The 1908 Tunguska explosion in Siberia was likely an asteroid impact. It flattened 2,000 square kilometers of forest instantly. Oh, and every million years, Earth gets hit by asteroids over 2 kilometers wide. Such impacts equal 100 billion tons of TNT, killing most people. The dinosaur killer asteroid was over 10 kilometers wide, happening every 100 million years. That would doom humanity, too. Note, every 100 million years doesn't mean we must wait that long. It means, during humanity's time on Earth, it could strike any time, just with tiny odds. What would such an impact look like? Scientists think Mars might have hosted life before Earth, but 4 billion years ago suffered a catastrophic collision. The asteroid hitting Mars was 2,000 kilometers wide, Pluto's size.
This impact likely wiped out Martian life and gouged Mars's northern hemisphere, covering its surface in magma.
Even after 4 billion years of healing, Mars's north remains dented compared to the south. That makes Mars the least spherical planet in our solar system. Lastly, even if Earth avoids collisions, our sun will eventually die. In billions of years, the sun will swell into a red giant, its edge reaching Earth's orbit, swallowing it whole. That's why humans must explore space to find new homes. Sagan believed achieving this requires human unity. Space exploration demands massive resources. Take unmanned probes. The probe itself costs about like a luxury sports car. But launching, controlling, and research require huge manpower and costs, many times over. Oh, the probe itself is one thing, but sending humans into deep space? That's a massive, costly system. Take America's Apollo program. Just landing on the moon required the whole nation's effort. It cost billions and involved over 20,000 companies, 200-plus universities, 80-plus research institutes, and 300,000-plus people. Sending humans beyond the moon demands resources no single nation can shoulder. Yet today, many countries pour vast resources into military conflict. The U.S. spends hundreds of billions yearly on defense. Only by uniting can we redirect military budgets to space exploration for real breakthroughs. So, what should humanity's space exploration goal be? Sagan believed the near-term goal must be sending humans to Mars. We've built the ISS orbiting Earth and landed on the moon. But that's not nearly enough. ISS research could be done by satellites and AI. Its real value is having humans aboard. Currently, humans stay months on the ISS, some over 2 years, studying physiological changes for long space journeys. If we never go beyond Earth, the ISS loses its purpose. As for the moon, no atmosphere, no water, unsuitable for settlements. Plus, if Earth suffers disaster, the moon's doomed too. So, lunar return shouldn't be the goal. Mars is humanity's most viable near-term landing target. Though lifeless, it's the most Earth-like planet in our solar system. And it's relatively close, just months away. Despite its bleak appearance, advancing tech could let us terraform Mars gradually. For instance, Mars is cold, but adding CO2, CFCs, or ammonia could warm it. Bioengineered plants could produce oxygen and food for survival. Just like humans once transformed barren lands on Earth, Mars will one day become habitable too. The longer-term goal of human space exploration should be to venture beyond our solar system, constantly seeking better homes for humanity. This way, billions of years later, when the sun becomes a red giant and dies, humans can still thrive. That wraps up the book's third part. Where is future space exploration headed? The goal of humanity's future space exploration should be sending humans into deeper space to find new homes. This is both humanity's inherent nature as wanderers and a necessary choice against earthly catastrophes.
To achieve this, humans must unite. It's the only way forward.
And with that, we've covered the main content of Pale Blue Dot. During the Apollo missions, it was Sagan's suggestion that made astronauts look back and capture Earth's first full photo, the very one on WeChat's launch screen. Sagan wanted humanity to leave Earth for new space homes, yet he always cherished our planet deeply. He described our pale blue dot in the book. In the vast cosmic arena, Earth is a tiny stage, but it's home. Everyone you love, know, or ever heard of live their lives here. All right, that concludes our interpretation of Pale Blue Dot. Reading notes are below the audio. See you next time.